So last time we were doing an example where we were talking about the correlation and the covariance between random variables, and we found out just through an example that the covariance between two random variables in our example turned out to be -1/144. So how am I supposed to interpret this? Is this good or bad? Is it big or small, right? Generally, the bigger the covariance is, the more that x and y are kind of related to each other, but I don't really know whether this is big, right? What I really want to do is normalize this so that I can kind of have on a scale that always is basically from -1 to 1, how correlated are things. And so for that, we define what's called the correlation coefficient. And that's called rho. Rho is defined as the covariance divided by the standard deviations of x and y. And remember, the standard deviation is the square root of the variance. Okay, so hopefully by now you should have some sense of these definitions, right? So the nice thing is that this correlation coefficient is always between -1 and 1. So this gives us kind of like a nice uniform way to kind of look at this and get a sense of its scale, right? So let me just kind of prove quickly why that's true. So let me start with proving something that is not really immediately obvious why it's related. So here is an expected value I'm going to compute. And I'm going to have a plus or minus here. So suppose I want to compute this expected value, right? Since I'm computing the expected value of some squared thing, we know that that has to be positive or non-zero, right? So now let me take this apart. I've got basically the expected value of this thing, and I've got plus or minus 2 times the expected value of this thing. And I've got plus the expected value of this thing. Okay. Now I say, well, actually, hey, this is just, if I had this would be sigma squared, right? So here, the expected value of this thing is just 1. The expected value of this thing is just 1. This thing in the middle is actually what we defined as the correlation coefficient, right? It's like the correlation divided by xy. So this is actually plus or minus 2 rho. So what we learned was that 2 plus 2 rho, plus or minus 2 rho, is greater than or equal to 0, which is a different way of rearranging this to say that plus or minus rho is less than or equal to 1, or rho is, less than or equal to 1 in absolute value. Okay? So how do I interpret the rho once I compute it? So how to interpret this correlation coefficient? And if I'm being really, precise, sometimes you may see it with rho underscore xy to indicate that this is the correlation coefficient just between these two random variables. Sometimes it's obvious, but other times you have to specify. So if I have 0, right, that's the same as saying that x and y are uncorrelated. So we talked about that last time, right? If I get exactly 1, either plus or minus 1, that means that y is completely predictable given x, right? If I tell you x, there's like 0 randomness in y. So y is completely predictable given x. There's no uncertainty there at all, right? If I'm somewhere in the middle, right? So if, for example, I have a positive correlation coefficient, what that means is that if x is above its mean, then y is likely to be above its mean also. Okay? And kind of conversely, if the correlation coefficient is less than 0, that means that if x is above its mean, y is likely to be below its mean. Okay? And an easy way to visualize this kind of stuff is with kind of a scatter plot, right? So what I could do is I could collect lots and lots of data, and I could look at how is that data distributed in the XY plane, right? So if I have a situation where the data is basically, looks like a circle, for example, where there's no obvious connection between X and Y, this would be kind of like what I might see, for example, if I had rho equals 0. If I had rho equals 1, this would be like saying something like this. I mean, there may be some variance in what's going on if I project it down to the axis, but there's like a one-to-one correspondence between telling you X and getting Y, right? So it's like the line, there will be a line that immediately connects the 2 points, or the two X and Y. If I have a positive correlation coefficient, kind of what I expect to see is something like this, where there's randomness in both variables, and the slope, if I were to draw kind of a best fit line through there, is positive. And kind of the other way around, if I have negative correlation coefficient, then things are more like this, something like that. Okay. So, let's think about some real-world cases where these things come up, right? So, for example, I may have a positive correlation coefficient between the image quality measured using some, JPEG quality, and the bandwidth that it takes me to transmit that image. Both of those are random numbers, but if the bandwidth is higher, then it's likely that the image quality is higher. You may say that the height of a child is positively correlated with the height of its parent. The complexity of an algorithm is positively correlated with the length of the code it takes to write that algorithm. Or, I might have a negative correlation to say, the heavier my car, then the lower my miles per gallon is, right? The more TV I watch, the lower my grades are, right? You can prove this at home. So, that kind of makes sense. And I'll talk a little bit in a lesson or two from now about, you may remember that we used this rho, this correlation coefficient, when we defined the jointly Gaussian random variable, and that was no coincidence that rho is related to the Gaussian. So I'll talk about that in the context of how the Gaussian looks in a lesson or two from now. One thing that I want to remind you is that, remember that we showed that if two random variables were independent, then they were uncorrelated. But remember that if two random variables are uncorrelated, that does not mean that they are independent. Okay, so that's one thing to keep in mind. This is a very common trick question on a test or something like that, right? And so one example that kind of shows that, and I'm not going to derive it again, because I think I did it in a previous video, but for example, let's suppose that I have a random variable that is uniformly distributed inside this square. Okay, so we showed, kind of by symmetries, I can see that, the expected value of xy is going to be right in the middle, and the expected value of x and the expected value of y are also going to be 0, because if I were to project by integrating these, squish all this probability down onto the x-axis, I get something like this, right? And it would also be centered around 0. So these random variables are uncorrelated, right? Because mathematically, this equals the product of these things, right? Both of those things are 0. But these random variables are not independent, right? We can show that, I think the example I used before was, consider this point out here. This has joint PDF equal to 0. I can't possibly get that point, but it is possible to get this value of y or this value of x. Both those things have non-negative probability, so I know that this is not true just by that counterexample, right? So here's an example where, I'm uncorrelated but not independent. So that's kind of an important thing to keep in mind, is that just because there's no how do I want to say this carefully? Just because it appears there's no relationship between the random variables from this kind of mathematical point of view, it's still possible that they're independent. And so this is starting to tend a little bit more into how do you interpret things like statistics in the real world. Like you've got a plot of this and a plot of that. Are they correlated? Are they independent? Those actually have some bearing on more like social science issues. And so we'll talk a little bit more about those implications in some future lessons.